It's Mrs. Mafucci, and it's time to continue our discussion of acids and bases. There are two different theories of acids and bases that we are going to be considering this year. The first one is called the Arrhenius Theory. Svante Arrhenius was a Swedish scientist who arrived at this theory back in the 1800s. According to Arrhenius, an acid is a substance that produces hydrogen ion in water. Remember that as soon as the hydrogen ion is formed, it combines with water to produce the hydronium ion. Arrhenius did not know about the hydronium ion, but his theory is still a good one. An acid is a substance that produces hydrogen ion in water. Hydrochloric acid, for example, produces the hydrogen ion and the chloride ion. Nitric acid also produces the hydrogen ion and the nitrate anion. The hydrogen ion is the characteristic ion that all Arrhenius acids produce when they dissolve in water. And the more hydrogen ion produced, the stronger the acid. We have already considered what determines the degree to which hydrogen ion is produced. The more the acid ionizes and produces hydrogen ion, the stronger the acid. The more the acid ionizes, the more the reaction lies to the right, the greater the equilibrium constant, and the stronger the acid. A base, according to Arrhenius, is a substance that produces OH ion in water. OH is the hydroxide ion. The hydroxide ion is the characteristic ion that all bases produce in water, according to Arrhenius. Consider sodium hydroxide. When it dissolves in water, it produces the sodium ion and the hydroxide ion. Calcium hydroxide also dissolves in water to produce the calcium 2+ ion and the hydroxide ion. The more hydroxide ion produced, the stronger the base. Now, the more soluble the base, the stronger the base, because the more the base dissociates and forms the hydroxide ion. Notice the two equations. Sodium hydroxide is a very soluble base. That means it completely dissociates to produce sodium ion and hydroxide ion. When calcium hydroxide dissolves in water, because it's relatively insoluble, an equilibrium exists between the dissociated ions and the solid calcium hydroxide. Because calcium hydroxide is not very soluble, it is a weaker base than sodium hydroxide. In an earlier discussion on acids and bases and their properties, we learned that acids and bases neutralize one another. In general, acid plus base yields salt and water. This is true for all Arrhenius acids and bases. All neutralization reactions are, in fact, double displacement reactions. For example, Consider the reaction between hydrochloric acid and sodium hydroxide. The products are sodium chloride and water. In this reaction, the hydrogen and the sodium change places with one another to produce the salt sodium chloride, and when hydrogen replaces the sodium, you get hydrogen hydroxide or water. Consider this neutralization reaction. Hydrochloric acid plus magnesium hydroxide produces the salt magnesium chloride and water. Remember, a salt is anything held together by ionic bonding. Magnesium is a metal, chlorine nonmetal. This would be an example of an ionic substance or a salt. Consider the reaction between sulfuric acid and sodium hydroxide to produce the salt sodium sulfate and water. Acids and bases neutralize each other, producing a salt and water. Neutralization is an example of a characteristic reaction between an Arrhenius acid and an Arrhenius base. The pH scale is a way of expressing the concentration of acids and bases. The pH scale is used for dilute solutions, and the pH scale ranges from 0 to 14. If the pH of a material is less than 7, it is considered an acid. If the pH is equal to 7, it's neutral. And if the pH is greater than 7, it's a base. Oranges have a pH of about 3.8. That makes oranges acidic. Ammonia, on the other hand, has a pH of 11, meaning that ammonia is basic. Let's now look at water. Since the Arrhenius theory has to do with the dissolving of acids and bases in water, it makes sense that we have a better understanding of water. For example, does pure water conduct electricity? Acids and bases are strong electrolytes. When they dissolve in water and either dissociate or ionize, they produce ions that are able to conduct electricity. But what about pure water? Water is a very, very, very weak electrolyte. That's because instead of producing ions, water establishes equilibrium that lies far to the left. In other words, in a sample of water, you have mainly water molecules and a few dissociated hydrogen ions and hydroxide ions. Well, how are the concentrations of hydrogen ion and hydroxide ion related in water? We have found that if you multiply the concentration of hydrogen ion times hydroxide ion, you will always get 1 times 10 to the minus 14. This is the equilibrium constant for the dissociation of water. This small equilibrium constant shows that the equilibrium lies far to the left and there are more water molecules present than ions. In pure water, the concentration of hydrogen ion must be equal to the concentration of hydroxide ion. In other words, x squared equals 1 times 10 to the minus 14, which means both the hydrogen ion and hydroxide ion in pure water is 1 times 10 to the minus 7 molar. This is considered neutral, and at 25 degrees Celsius, this has a pH of 7. When water dissociates to produce the hydrogen ion and the hydroxide ion, that hydrogen ion automatically combines with another water molecule to form the hydronium ion and the hydroxide ion. This is referred to as the autoionization of water. The equilibrium constant is the same as what we saw on the previous page, because remember, hydrogen ion is, for all intensive purposes, equivalent to hydronium ion. If you multiply the concentration of hydronium ion times hydroxide ion, you get 1 times 10 to the minus 14 at 25 degrees Celsius. This is the equilibrium constant, the KEQ for water, also known as the KW. In a neutral solution, the hydronium ion concentration must be equal to the hydroxide ion concentration. Therefore, both have a concentration of 1 times 10 to the minus 7 molar. Let's now look at how we can calculate the pH of a solution. pH is defined as the negative logarithm of the hydrogen ion concentration, or hydronium ion concentration. Now remember, the hydronium ion concentration times the hydroxide ion concentration is equal to 1 times 10 to the minus 14. Therefore, if the hydrogen ion concentration, which is the same thing as hydronium ion, is equal to 1 times 10 to the minus 8 molar, this means this solution has a pH of 8. The hydroxide ion concentration would be equal to 1 times 10 to the minus 6 molar, with a pOH of 6. This solution with a pH of 8 greater than 7 means this is a basic solution. If, on the other hand, the hydrogen ion concentration is 1 times 10 to the minus 3 molar, it has a pH of 3. This is clearly an acid. If the hydrogen ion concentration is 1 times 10 to the minus 3, the hydroxide ion concentration must be equal to 1 times 10 to the minus 11 molar. This has a pOH of 11. pH plus pOH is always equal to 14.